So can everyone see my slide now? Okay. Yeah. So yeah, let's continue discussing the neural rendering. So far, what we have discussed in this class is about basically some different representations and some kind of the neural net the architectures that can encode, decode some kind of those representations. And from the last week and also from the week before the last week, we started to discuss like how we can basically do some kind of the image to 3D reconstruction. Especially for the multi-view image cases, we could do this kind of 3D reconstruction even without using any neural net. But for some kind of the obtaining some kind of the clean images from the arbitrary views, we started to discuss the ideas in terms like training some kind of the implicit neural representations while encoding the kind of the occupancy and the radiance information in a way that we can render this kind of some implicit 3D kind of things into the images through the volume rendering the equation. Please mute. Sorry. Let me check that. Please mute. Okay, so yeah, so we have briefly discussed like two different approaches for the neural rendering. The first one was the deep voxels, which is basically representing everything as kind of some latent features for every the kind of voxel in this 3D space that we are defining some kind of a 3D grid, right? And the other one was basically the neural radiance field. And the major differences from the nerve from the kind of the deep voxels is that first, we are not using some kind of these 3D voxels, but we are basically having some representing everything as kind of the implicit deep functions. And the other kind of very important thing is that we are not basically predicting some kind of the occlusion kind of the weight. So everything was basically linearly the combined in the deep voxels. Basically, we are predicting some kind of the weight for the linear combination, and all the features along the lay were basically linearly combined with some kind of the weights that we are basically also predicting using the neural net. But instead of that, like we are basically using some kind of the classic the volume rendering the equation in the nerve case. And the other thing is that we are also basically encoding some kind of the view-dependent color information. So this was the case that we are somehow explicitly basically predicting the color information, basically having some kind of the latent features that will be decoded. But the thing is that the colors are basically view-dependent color because like we are not having the information about some kind of some shading, lighting kind of things. So instead of like modeling some kind of the environment about like the shading and the shadow kind of things, we are directly encoding all the colors as some kind of the view-dependent information, which was also called the radiance, right? So that's why this is called the neural radiance field. Okay? So in the neural radiance field, in short, the nerve, we are basically having the two, the implicit representations. Like the first one was basically the radiance map, which is taking the position and also the view direction information. So this is the case that we are taking 5-dimensional vectorized input, the x, y, z for the position, and the another the two, the dimension for the view direction, and then predicting the RGB, the color, right? So basically simple the architecture, taking 5-dimensional vector as the input and predicting the 3-dimensional the output. Right? And the other one was basically the opacity map, which is taking only the position information and then predicting the the negative, some kind of the opacity, the information. And the key of the opacity is that this is basically the information which is also used to calculate the transparency. So what we have seen last time is that the opacity is giving the information about like how likely the ray will be terminated at a certain point, how much the ray will stop at some kind of certain point. And based on that, like the kind of the notion that we are introducing here is also kind of the transparency, which is also about kind of the some probability about like how likely the ray will not stop until that the point. So you can see that the formulation is also defined based on the opacity that we are defining here. So by combining these two, now we can calculate some kind of some sort of the probability in terms of like how much the ray will not stop until that point, and then stop at that certain point. So it becomes some kind of the weight for the radiance that we are also predicting using the another neural net. So you can see that now the color is basically somehow defined as kind of the expected value for the radius, while basically calculating the probability in this way. And we have seen that the transparency is having this kind of exponential form, basically taking the integral of this some kind of the opacity along the array. So from this formulation, so we are going to see how this formula has been derived. But from this formulation, basically what we have seen is that, as we also discussed last time, the first thing is that this basically is like this definition is aligned with some kind of a physical concept of the transparency. In terms of that, at the very beginning, you can see that the transparency becomes 1. So obviously, there's no reason that the array basically stopped at the very beginning, right? So the probability starts from the 1. And over time, it's basically decreasing. It's basically non-increasing function, right? So over time, basically, the transparency is likely to be decreased because there is like more chances to be occluded by some kind of the occluders in this space, right? So it's basically like it's aligned with some kind of physical concept in terms of that it's basically in the range from the 0 to 1, and then starting from the 1, and also it's becoming some kind of the non-increasing function. So it's basically likely to be decreased over time. So in that sense, basically, it's basically aligned with some kind of the meaning of the transparency, while the direct prediction of the occlusion kind of weight for the deep voxels could basically break this kind of some kind of the physical rules in terms of that some points that are behind of the other point can be more visible, right? But there is no such kind of a case this kind of the formulation. Make sense? Any questions on this? So we are going to briefly see basically how this formulation has been derived based on some kind of the modeling, some assumption for some kind of things that we are doing. So basically what we are going to say is that we are basically shooting a ray. And let's think like the ray is kind of so we are modeling the ray as kind of the very thin cylinder in the 3D space. And the ray is basically passing through some kind of the media where there are some kind of the particles that might basically occlude some kind of the rays that we are shooting. So let's think about that. This is some kind of the slice of that the cylinder in the 3D space. So each of basically the slice, what we can see is that basically there are some kind of some small, tiny particles that are basically also modeling some kind of something that may basically occlude this kind of the ray marching. Okay, so let's say that we are basically having some kind of the tiny particles with some kind of some density here. So these are basically indicating some like how many kind of the particles will exist in the space. So if we basically multiply this density with some kind of the certain volume in the 3D space, that is basically giving some kind of the sort of the expected number of the particles. So let's say the rho here is the density, and obviously here the E is the area of the section here. And the delta T is basically the time of the kind of what's the time the ray flies in the 3D space, and which is also corresponding to kind of the distance of the height of the cylinder here. Okay, so when you multiply the area of the section here, E to the delta here, this is giving the volume here of this kind of the slice of the cylinder. And when you multiply the volume with the density, this is giving the number of the particles, basically some kind of expected number of the particles. Makes sense? And also let's think about that. We are basically modeling each of some kind of the tiny particle as some kind of some sort of a sphere. Or it doesn't need to be sphere, but let's say it's kind of a sphere in terms of that. When you see this kind of the particle from the certain direction, the projected area of those kind of the particle through with respect to some kind of the specific direction is giving some kind of the projected area. Which is in the case that when you model the particle as some kind of some sphere, then we can see that the projected area is kind of the area of the gray circle here. So let's say like this is kind of the A here. And basically then based on that, what you can see is that the ratio of the occluded area along this kind of some specific direction can be calculated in this way. So basically what we can see is that the numerator here is basically showing some kind of the sum of the area of some kind of the projected the sum of the projected area of the particles here. Okay, so we are basically multiplying the A with by some kind of number of the particles here. So you can see that this is kind of the sum of the projected area of all the particles that are basically existing in the inside of the slice. Okay. Over the E was basically area of the kind of the section here. So basically, this is showing some kind of the ratio of like how much the region, some kind of projected region is basically occluded by the particles. Make sense? So we can say that this basically shows the ratio of the occluded area. So we can cancel out the E here, and we can have the like this kind of notion. So what you can see is that this kind of the ratio of the occluded area is basically having some kind of the correlate with some kind of delta T here. So what we are going to do is that we are going to define the A times the rho T, basically the projected area multiplied by the particle d density as kind of the extinction the coefficient, which basically means like how likely the ray will be occluded with any of the particles here. So when you basically multiply this kind of term by some kind of delta T, how much the light flies in this kind of the small d section, this gives some kind of the ratio of like how much the ray will stop in this specific the slice. Okay. So this is basically the term that we are basically defining as kind of the opacity. So this is kind of the exact definition of the opacity that we are defining with the neural implicit function. Okay. So which is now denoted by the sigma here. So which is basically having the meaning that it's like multiplying the project area by the particle density. So you can see that instead of like we are defining the particle density, we are directly defining the opacity in terms of that the ratio of the occlusion can be calculated by multiplying this by the delta T here. Make sense? So based on that, like basically how we can define the transparency is that transparency was basically the probability of like how likely the ray will not stop until that point, right? So this basically what this means is that the probability of that the ray will not be terminated until the time of the t plus delta t is the same with the probability basically the ray does not stop until the time t, and also does not stop during this kind of a period in this section, in this slice. So the probability the ray will not basically occluded in this slide will be 1 minus this term, right? So because like this was kind of some probability of like how likely the ray will be occluded, basically this term inside this slice, right? So if we take the 1 minus this term, which is basically the same way like this one, this basically shows that the probability of like how much the ray will not basically be occluded with any particle in this slice. So the meaning of like, let me switch to the pointer. Yeah, so the meaning of like this term is that we are basically multiplying the two probability, how much the ray will not stop until the time t, and also how much the ray will not be occluded in this given the section, the slice, right? Then we're gonna basically get this term, right? So from this, basically what we can see is that this is basically showing that it's kind of the ODE formulation in terms of that what we want to do is that we want to get the function of the t, capital T here, right? But function of the capital T is also defined with some kind of the gradient of the transparency of the function here. So in terms of that, we can see that this is kind of the ODE formulation that the given the function and also its gradient is having some kind of some linear the equation like this. So if you basically divide the left term and the right term with respect to by the kind of delta t here, then you can see that the transparency function here and also its the gradient is making some kind of linear equation, right? So we just need to basically solve this kind of like the ODE formulation. But we are having some kind of some initial condition in terms of at the very beginning, we know that the transparency should start with the 1 here, right? So given this kind of like initial condition, if we solve this ODE formulation, then we can see that the transparency function t should have this kind of exponential form. So you can check this out. So this was basically the things in terms of like how we derive this kind of formulation in the previous slide. How do we handle a situation where one particle is occluded by another? Yeah, so that's really a good question. So here also the question is that would there be some kind of the cases that some particles are also occluded by the other particles? This is really good question. So we are not actually precisely modeling all those kind of things. Actually, there can be also some cases that the particles can be also occluded each other. So actually those kind of the factors should be actually incorporated in this formulation. But in this simple kind of the modeling, we don't care about such kind of the cases. But there would be some kind of the more precise way to model all these kind of some complicated situations. So you can assume that this is kind of like some sort of the very simple simulation with some kind of some lots of the assumption and also basically not handling any kind of the complex situations. Any other questions? Yeah. So many kind of assumptions that even the particles are kind of these pairs, but we don't know, right? But it's basically a matter of like how we're gonna basically derive some kind of the forms of the transparency with the definition of the extinction coefficient or the opacity. Any questions on this? So you can see that this is basically some kind of the analytic form in terms of how we can calculate the color for each of the ray by taking the integral, actually taking the integral twice over some kind of the time domain here. But for each of the time t, we also need to take the integral to take compute the transparency here. But basically showing some kind of the analytic form in terms of how we can determine the color rate of the ray based on the function of the opacity and also the radiance. The color information depending both on the position and the view, the information. So here the question is that how we are going to implement this using the Python code. Because we know that basically these function, the opacity and the radiance, these are basically neural net, right? So what we can do is that we can basically query some kind of the points and also the viewpoint information, and then get some of those kind of the opacity and the radiance information. But how can you take the integral with this kind of the neural net functions? This is kind of the problem in terms of the implementation, right? So in terms of like implementation, basically what we are going to do is that obviously we are going to do some kind of a sampling. We're going to do some sort of the discretization and basically approximating the integral, the kind of the formulation. So the kind of some basic approach for this is basically using some kind of the stratified sampling the idea, which is basically nothing but we are dividing the time domain of the ray with some kind of the uniform interval. So if we shoot a ray in this 3D space, we divide some kind of the time domain, the distance of the ray with some kind of uniform interval. And then for each of the interval, we are sampling one point, random point within that kind of the beam of some kind of the split, some kind of the time or the distance space. Please mute. Yeah, so that's the kind of thing. So once we basically take like one sample for each of the beam, we can assume that all the opacity and the radiance information inside that beam is the constant with the information that we are getting from the representative sample there. Okay. So that's the basic idea for the stratified sampling. Makes sense? We are basically dividing the time domain with uniform interval. And for each of the interval, for each of the beam, we take some kind of the random point within the range of the beam. And then basically given the query point, we get the opacity and the color information. And then we simply assume that the opacity and the color inside that beam is basically the same, the constant with the value. So that's the basic idea. And based on that, we can actually calculate the transparency at the beginning and also at the end of that beam. Yeah, basically by just taking this kind of the things. So we can see that this is basically the some kind of the transparency based on the assumption that the opacity and the radiance will be basically the opacity will be basically the same constant inside that bin. So based on this kind of the some approximation, basically what we can see is that given this kind of the integral, now we can basically approximate this kind of the integral in terms of like this way by setting some kind of the bins here. And then from each of the bin, what we can see is that obviously the radiance and the opacity, these two are basically constant like this. We can set them to the constant. But for some kind of the better approximation, so what we can also do is that simply, as we basically assume that the opacity and the radiance are basically constant for each of the bin, we can also assume that the transparency is also constant for each of the bin. But actually, we can say that even when the opacity is basically the same within the bin, the transparency will be decreasing during the kind of the same bin, right? Because like if we are having some kind of a non-zero the opacity inside that bin, then the transparency should be still decreasing over time. So some kind of the better way to more precisely approximating this equation is not to take the transparency as to be the constant inside the bin, but still calculating the transparency based on the constant, the opacity and the radiance information. So this is kind of some small kind of thing in terms of that. While we assume that the opacity and the radiance to be the constant, we don't assume that the transparency is not constant, but it's really just calculating this based on those two, the sample, the values, okay? So basically what we can briefly see is that, so here basically what Ci means is that it's basically the integral for each of the bin. So for each of the bin, we are taking the integral of the whole equation. So by taking the sum of those kind of the integral for each of the bin, we will be able to get the color for the ray. And inside each of the bin, obviously what we can see is that this radiance and the opacity will be constant. So we can take out those kind of terms outside of the integral. But what we can see is that when you basically calculate this transparency term here, we are dividing this term into the two integral. Like one is like the integral until the beginning of that bin. So for the integral for the until the beginning of like this bin, we also introduce this notion of the capital Ti. So we can basically just like replace this part with the Ti. So this is like what we defined in the previous slide here. So this basically indicates some kind of the transparency until the end of each of the I spin. So when you take the integral from the Ti to Ti plus 1, we can divide the transparency term here into the two integral. And the first integral can be calculated with some kind of the Ti, capital Ti that we have here. And the second, the integral can be just literally calculated by the constant sigma I here. We assume that the sigma is basically constant inside that bin, but the transparency is still decreasing if the Ci is basically non-zero the value, okay? So then we are basically having this kind of the additional term here. So what we can see here is that the Ci is the constant, the radiance from this this range of the bin. And then we are having the Ti, the transparency, which is until the beginning of that bin. And also we are having the additional term, which is calculated by taking the integral of the transparency within that bin, right? So basically like having some kind of the additional term because we are assuming that the transparency is basically not constant, but the two terms are basically constant, okay? So, and this is giving some kind of probability of like how much the ray will basically stop at some kind of the point, in certain point within that kind of the bin. So by just like taking this summation, basically we are calculating the transparency for each of the end of the beginning of the kind of bins in this way by defining this we can now calculate the color for each of the radians by taking the sum like this, based on some kind of samples that we are taking for each of the beams along the array. Make sense? So if this is basically not sure, you will need to check out some more details about this formulation and see how exactly we need to like implement these kind of things, because like implementing this will be part of the assignment too. And you will see how exactly we need to basically calculate those kind of things. Okay? So check out the meaning of like each of the term and see why we are having each of the terms here. So this is like all kind of the basic idea in terms of how we can calculate the Boltzmann equation with the sampled points. How many beans are typically used in the real world applications to produce well-formed graphics? So you will see. So you can, in the assignment 2, you will be able to see how many beans that we set there. Actually, the number of the beans will also depend on some kind of the scale of the kind of the scenes and how much it is some kind of details that we want to capture in the 3D scenes. But for those kind of some details for the parameters, I'd like to let you basically check out some kind of details in the code that we have. The remaining question is in terms of the implementation. So how we are also going to make some kind of neural architecture, the neural network architecture for the implicit neural representations, right? We had that the implicit representations, like one was for the opacity and the other one for the radiance, right? So the interesting thing is that typically this kind of the architecture is being used for the neural rendering, for the nerve especially, which is actually you can see that it's basically having a single architecture, single neural net. In a way that basically in the kind of the NLP, the architecture, at the very beginning, we are having the position information here, and actually here, two position information, and then having the view direction at this point. And having basically the location information here with some kind of the multiple layers, we are getting the opacity as the kind of the output from this layer. And some kind of with some kind of few more the additional layers, we are basically having some kind of the radiance information here. So it doesn't need to be basically specifically this architecture. This was the architecture that's been proposed by the people who invented the neural radiance field. But you can see that actually it doesn't need to be specifically this architecture, but you just need to have some kind of any arbitrary the NLP, the networks to predict those kind of two quantities. But here are basically a few kind of things that are quite important in terms of like implementing those kind of things. The first thing is that basically we are having some kind of the gamma function here. Can you guess what's this like the gamma function here? So actually, we have seen this in the previous lecture when we were discussing the implicit representations. So this is basically the sinusoidal the functions, the Fourier features, which is also called the positionality encoding. So here the 6t and the 24, those basically mean that we are basically mapping some kind of here the XYZ three-dimensional input into the 6t dimensional vectors here, using some kind of by having the 6t number of the sinusoidal functions with all different frequencies. This also means that we are mapping the two-dimensional input vector, the view direction of the information, into the 24-dimensional the vectors with this kind of cosine and the sine the functions. So basically some kind of the mapping function, which is basically mapping the low dimensional some kind of information into the much higher dimensional some kind of the vector, while basically varying the frequency of the sine and the cosine here. So here basically what we can see is that the first thing is that we are mapping the XYZ coordinate into the much higher dimensional the dimension of the vector, 60 dimension, while for the view the direction we are mapping into the relatively lower dimension of the vector, 24 here, right? And when you also see, like when we basically feed the input of the location and also output the opacity here, and also feed the view direction information and also get the radiance here, the location to the position to the opacity is much deeper. It is having some multiple layers, lots of the layers from the input to the output, while for the view direction to the radiance, we are only just having like two directions, only having the two layers. So having some much shallower kind of the network for the radiance deep prediction. So that's kind of some characteristics of like this kind of architecture in terms of that we are mapping the XYZ coordinate into the much higher dimensional kind of the space, and also basically making the deeper the network. And the reason for that is that typically the function of the opacity with respect to the position would be more like rapidly fluctuating the function, which means that it will be higher in frequency the functions. Because if we see the meaning of the opacity, the thing is that while we use the volume rendering the equation, for most of the cases, what we are reconstructing will be some solid the object, right? So having the solid object means that the opacity should be basically close to zero for the kind of empty space, and it should be higher number for some kind of some inside region. So this also means that like for some kind of the boundary of the object, for the surface of the object, this kind of opacity should be rapidly changing from the very small number to the very high number in some kind of very small region, right? It should not be basically smoothly increasing near some kind of boundary region, but it should be some kind of the step function kind of things, right? Zero for some reason, but if you move to the next point, it should be basically one, close to one or something. So which means that the opacity function is expected to be high frequency function because that's also the reason like why we are basically mapping the position into the higher frequency sine and the cosine function in terms of like having some kind of the high dimension in the position encoding, and also making the network to be deeper because the function that we are going to learn is expected to be high frequency function. Make sense? But how about the radiance? Especially like when you see the kind of the radiance with respect to the view direction. For the respect to the view direction, we don't expect to see some kind of the very rapid changes of the color across some kind of views. So obviously there might be some changes of the color depending on the view direction because of the lighting and some kind of the other some environmental information. But for many of the cases, like when you see some kind of the skin color of like my face, like depending on like which view you are seeing my kind of the some same point over my basically the skin, it's not expected to see some kind of the seeing very different color, right? It might be still something like the skin color kind of things, which means that the radiance function, especially like with respect to the view direction, will be smoother function. It's not rapidly changing, but basically changing smoothly over the changes of kind of view directions. For those kind of the smooth function, for some kind of the low frequency function, what we are going to do is that we are going to basically make the neural network like shallower, having some smaller the parameters to be the optimized, and also the mapping some kind of input into the lower frequency sine and the cosine function. In terms of that, we can basically avoid some kind of the overfitting to kind of the data that we have. So that's kind of thing. So when you basically expect the output function that we are basically learning to be basically high frequency the function, basically some rapidly fluctuating the functions, we're gonna make the neural network to be deeper, and also do some kind of position encoding with the high frequency sine and cosine function, basically increasing the dimension of the position encoding. In terms of that, we can properly learn this kind of some kind of fluctuating the functions with this kind of architecture. But when you expect that the output function is to be a smooth function, some kind of low frequency function, then we basically also reduce the number of the parameters of neural net in terms of like making the network to be shallower, and also using the position encoding with the low frequency sine and cosine functions, basically decreasing the dimension of the position encoding. In terms of that, we can avoid some kind of overfitting for the smooth functions. Okay? So this is basically the reason like why we are having this kind of the architecture to learn the opacity and the radiance. So as I said, it doesn't need to be this specific architecture. But the reason like why we're having the deeper kind of the layers for the opacity and the shallow the layers for the radiance are basically because of those kind of reasons. So even when you basically want to tune some parameters of the neural net, you can consider these kind of effects. Okay. Here the question is that what is a expected difference between by concatenating sinusoidal location vector and using the sinusoidal activation function? So the only difference is that it's basically a matter of like whether you map the output of each of the layer into the sine and cosine function, or mapping input of the layer into the sine and cosine function. So it should not make some kind of the big difference, as I also mentioned last time. So that's kind of the only difference. The siren and the Fourier feature kind of thing is that it's just matter of like whether we're gonna map the output to the sine and cosine function or map the input to the sine and cosine function. But typically when you use the activation function, we only use the sinusoidal function. But here the thing is that when you typically map the input to the some kind of the sinusoidal functions, we can map this into the multiple sinusoidal functions, as you can see here. We are mapping into the multiple cosine and sine functions while basically varying the frequency here. So when you typically talk about the position encoding, increasing the dimension basically typically means that we are also mapping the input to the higher frequency sine and cosine functions as well, while also mapping them into the low frequency functions at the beginning. So the increasing dimension means that we are also using some kind of the higher frequency sine and cosine functions as well in the mapping, which will be helpful when the functions that we are learning is also kind of have some high frequency functions, right? So that's kind of some main difference. Makes sense? So there is no some kind of some theoretical some kind of guarantees here, but it's more of some kind of the implementation details in terms like how we can basically make the neural net to learn some kind of some high frequency functions or low frequency functions by the design of the architectures. Okay? So I strongly recommend you to play with those kind of things in the assignment too, and see how much this kind of some kind of the different design of the neural network also affect the final results. So that's also be interesting things to see. And one more some kind of trick in terms of like implementation is that so there are also some technique like the hierarchical sampling, which is basically having some kind of the two networks. So the first idea is that we are basically having some kind of the set of the samples with some kind of the bigger, some kind of interval of the rays in terms of we get some kind of the probability, like how much the ray will stop based on some kind of coarse samples over the ray. And then once we have some calculate this kind of the probability, like how likely the ray will stop for each of the point, then what we can do is that we can do some kind of the adaptive sampling again, using the another neural network. So which basically means that based on the probability we are calculating with the first network, now we can adaptively sample more points when the probability is higher. And also having some kind of the non-uniform, some kind of the bins in the ray while calculating the integral in the same way. So this kind of some refinement step with the two networks can improve also the reconstruction quality as well. So you can also check out those kind of the details in the neural radiance field paper, and also you can check out those things in the assignment too. I know that like implementing the hierarchy sampling is not part of the assignment too, but you can consider also implementing this as well and see how much this can improve the quality. So basically in the training, what we can do is that, it's kind of like simple the architecture in terms of that we basically batch the pixels, randomly sample some kind of the bunch of the pixels in each of the image, and sample the points along the array while basically having some kind of the intervals along the array, doing some stratified sampling, and then basically predict the radiance exactly, and also the opacity information for each of the points, and calculate the volume rendering the equation to determine the color for each of the ray, and basically compare that color with some kind of color that we have in the given the image, basically minimizing the L2 loss and running some kind of backpropagation. And this kind of the idea that we are using some kind of the implicit representation is and also directly encoding the opacity and the radiance information is like way more effective in terms of that we can basically better capture all the details of these 3D things while also using way smaller the amount of the memory. So only with some kind of the 5 MB of the storage that we are using, we can capture some more details compared to the some previous work. So that's kind of the things. And also based on some kind of the opacity and also especially the probability information, how likely the ray will stop, we can also calculate some kind of the estimate, some kind of the depths for each of the ray in terms of that we can get this kind of the distance information in terms of like estimating some kind of certain point where basically the ray will stop by setting some kind of the threshold for the probability. You can see some kind of some fine details that we are basically getting some of this kind of 3D reconstruction. So this looks like amazing, right? We can do this kind of like perfect some 3D reconstruction, not just getting some kind of some sparse point cloud, really, but just like enabling like rendering things into this some arbitrary viewpoint using some kind of the neural net. You can actually see that the architecture in terms of like implementation is also quite simple. Actually, it's very simple, just like having some kind of the MLPT networks with some kind of the loss function. So you just need to implement the Boolean equation. So with this kind of simple architecture, we can get actually the amazing results in terms of like 3D reconstruction. Looks really cool, but actually there are also quite many limitations of this kind of some basic architecture, and there are also lots of some following work, some research that happened in the last 5 years to basically also improve some kind of overcome some limitations of the neural network field. The first problem of the nerf is that actually it takes lots of time for training. So this is also something that you need to remember because like for the implementation of the assignment 2, actually the training will take some time. Might take at least like some hours. It's kind of like smaller things, but still it might take some kind of at least like some hours to train the things. So there will be some kind of the bottleneck in terms of like implementation. So even when you have some kind of the bug in your code, you might need to take some kind of the hours to see like what happens after you train all the things. So like the very slow the time for the training is kind of one of the biggest limitation. And there are lots of some kind of following work in terms of like how we're gonna basically overcome this kind of slow computation, the training time. And we can also see some kind of relevant work for that. And also how we are going to make it like scalable, not to reconstruct some kind of a small object or small scenes, but some kind of some bigger kind of things. So I also recommend you to check out like some other kind of like relevant work, like some block nerf was kind of the example to reconstruct entire the city. San Francisco's the city was reconstructed using like the nerf kind of the technique. You can also check out some kind of some related work in terms of like how we can also scale up the reconstruction into not some kind of the object in this small scene level, but in the level of some kind of the bigger scene or even in the entire city. And also the thing is that the neural radiance field obviously requires to have some kind of the accurate camera information. So we first need to have some very accurate camera information for each of the view. So also for the 3D rendering the contest, if you do something based on the neural rendering kind of things, you will see that the most important part is to first get some kind of the precise camera pose information. Otherwise, we won't be able to get any kind of some good quality of the output. So getting the accurate camera information is the first part. And there are some kind of following work that can also, that are trying to basically do some kind of some reconstruction without even the case that when there are some kind of the noise in the camera information. But while it's still very challenging kind of task. So you first need to get some kind of the camera information, the camera information. And also how we are also going to handle some kind of the moving objects or some dynamic scenes in the scene. So while you are taking the photos from all different views, if some objects are basically moving in the scene, there is no easy way that we can basically properly reconstruct all the things, right? So there can be also kind of so yeah, that's also kind of things that we need to consider. But there's also kind of be some recent techniques in terms of how we're going to handle this kind of like dynamic objects, okay? And also the lighting. So since we are basically predicting the radiance, which is basically incorporating all the light information. But what if we want to basically place the reconstructed object in the different, the lighting the situation, the lighting the environment. So it's basically changing some kind of the lighting the condition, right? So like enabling this kind of thing is not directly possible with the nerf the alphas, but there are also some kind of following work of like doing these things. And the other thing is that the goal of the neural rendering, as I mentioned at the beginning of the discussion, is that it's not about basically getting some kind of a precise, some geometry of these really things. It's more about basically getting some, actually, we are even seeing the solid objects as some kind of the, some volume, some media, where we are basically assuming some kind of some particles and some kind of occlusion kind of things, right? So there is no way that we can easily get some kind of very precise the surface information, while we can do some kind of the estimation of the depths using the probability that we are calculating. But there is also some kind of the more advanced work in terms of like, not just getting some kind of the some volume information, but directly getting some kind of the precise the surface information. So you can also check that out. And most important thing is that while we are using the neural net, this is not about basically training the neural net for some kind of the multiple the scenes and doing some kind of the achieving some kind of generalization for the unseen, right? So you can see that this is kind of the interesting the case that we are using train the neural net for one specific object or one specific the scene with a bunch of the images that we are having in the scene. So if we want to achieve some kind of generalization, that's kind of another kind of things. So we are not going to get into these kind of the details, but keep this in mind that we are with the typical the neural pipeline is basically having one neural network for the one scene or the one object. But how we gonna basically make the neural net for the that can like reconstruct the multiple scenes or the multiple objects is kind of the next topic. So that are basically also discussed in the many other some kind of the relevant the related work. And also more things in terms of improving the quality, making it conditional, some kind of reconstructions, composition, many kind of things. So you can check out some more details in this country in this link. Okay. So those are some kind of the introduction of the nerve. Any questions on this? So here the question is that what is the cause of the long training time? We're gonna get into that. So right now, after taking some questions. Any questions on the neural rendering, the nerve? So here the question was that, so why is it taking so long time to train the nerve, right? Obviously, the reason for that is that we need to basically encode all the opacity and the radiance information in the 3D space into a single neural net, right? So those kind of some opacity and the radiance information is basically the per point information in the 3D space. But those are basically encoded into the neural net parameters in a way that when you basically feed like one specific the query point, it can predict this kind of opacity and the radiance information. So it's basically a matter of like how we can make this kind of neural net that can basically encode this kind of the opacity and the radiance information. But here the thing is that before the nerve, we also have seen the case of the deep voxels, right? Which was actually the case that we are using some deep voxel representation, some 3D grid, and somehow storing some information per voxel, right? So here the question is that why don't you just like directly store the radiance and the opacity information per voxel without using any neural net? Isn't it doable? So that's kind of things about like what we are going to discuss with the hybrid representation. Actually, it's very doable in terms of that. Even we don't need to use the neural net. We can just directly encode, not encode, we just like store the radiance and the opacity information for each of the voxel in the 3D grid. And then the good thing for it is that it will be super fast in training. So let's think about that. We are basically revisiting the voxel representation and taking the 512 the cubic resolution. Then what we can see is that actually the training becomes way faster like this. Even in like few seconds, like we are already getting some kind of some 3D things, right? So this is really doable. So we are not gonna get into any details because of the lack of time here. But what we are doing is that for each of the corner point of the some 3D grid, and then we are basically storing the opacity the information. And then along the ray, if we have any kind of point over the ray, what we do is that we do some kind of the three linear interpolation by taking the 8 corner points of that basically the voxel that is including this specific point. So very simple the idea. Even there is no the need to basically have any neural net. We can directly basically store some kind of the opacity information for each of the corner point of the voxel and do some kind of the some linear interpolation for each of the point along the ray. So that's the simple thing. But here, like one remaining the question might be is that how about the radiance? Actually, radiance is not some kind of a scalar value for each of the point, but even when you fix the point in this 3D space, okay, radiance is kind of the function with respect to the view direction, right? And the function with respect to the view direction basically means that it's kind of same as kind of the function over the sphere, right? Because of the view direction can be treated as like one of the points over the unit sphere, right? So it's basically a matter of like how we're gonna basically store the function of the respective unit sphere for each of the corner point of the cell. And for that, like while basically skipping some kind of details here, what we are going to do is that we are going to represent the radiance function with respect to the view direction as kind of some sort of the linear combinations of some kind of the basis function. So here the very basic idea, if you are not familiar with speaker harmonics, is that the Fourier transform is basically all about basically representing all the signals as kind of the linear combinations of the combination of the sine and the cosine function, right? So as we do some kind of the Fourier transform, we can also define some kind of some sort of the basis functions over the sphere. And these basis functions are basically what we are using here is basically the speaker harmonics, some kind of allowing some kind of doing some kind of spectral analysis. But let's say like we are defining some kind of some basis functions defined over the spheres and representing all the radiance function as kind of some linear combination of like those things. So we basically specify the certain number of the basis functions, which means that all the radiance function will be represented as kind of set of the coefficients of like those basis functions. And then the rest of things is the same. Like we can just do some kind of we can first evaluate the radiance function with some kind of given the view direction and do some kind of the trilinear interpolation for each of the point. And this is giving some kind of really good quality of the reconstruction. And also it's like way faster and it's like 100 times faster than the nerve. What would be downside for this? I said that this is the results that we are using the 512 the cubic the resolution, which means that while we are basically speeding up the training, this will be the case that we are taking huge amount of the memory. So when we basically achieve some kind of same quality with some kind of the nerve using the 2.5 the megabyte, we will need that more than like 150 the megabyte for some kind of same quality of the outputs. So that's kind of things. We are seeing some kind of the trade-off between the computation time, the training time, and also the memory. So as we want to basically make it fast to train some kind of things, we're gonna need to basically have some kind of the larger the amount of the memory, right? So yeah, so the question was that what is the cause of the long training time for the nerve? And the long training time is not only because of the large number of the parameters of the training, but because of that, we need to basically encode all the opacity and the radiance information into the neural net parameters. But instead of like having the neural net parameters, if we spread out those parameters as some kind of the explicit the opacity and the radiance values for each of the points in the 3D space, we can make the training to be way faster. But the thing is that we are also sacrificing the memory efficiency. We are taking lots of the memory. So as kind of some sort of making some sort of making the balance between the computation time and the memory, So these are basically the two extreme cases. Like one is basically encoding all the information into the single neural net. And the other one is basically storing all the information explicitly for each of the corner point of the boxes, right? So the first one is very slow, but basically compact. And the second one is very fast, but memory heavy. So the kind of the way that we can make the balance between these two is that we are basically storing some kind of the latent features as we have done in the deep voxels. And then decoding this kind of the latent features with the very shallow the layers. So the meaning of this is that, so the meaning of like this is that when you have some kind of the deep network of the nerve with some the bunch of the layers in the nerve, we are kind of like taking the most of the parts of the neural net parameters as kind of the spatially aligned parameters. So what this means is that instead of like having some bunch of some kind of the neural network the layers, we are basically placing this kind of some sort of the latent features for each of the corner points. So the good thing for this is that when we update those kind of parameters for each of the ray, we don't need to update all the parameters in all the latent features for every single the voxel, because we only need to care about some kind of the voxels where the ray is basically passing through. The other some kind of regions where the rays are basically not passing don't need to be updated. Don't need to be updated, right? So this is kind of good thing in terms of like when you basically have some spatially aligned the parameters. Those basically means that when you basically have the latent features for each of the some voxels in the 3D space, we can see what are the parameters that are basically associated with which ray. So we don't need to basically update all the parameters at the same time with all the rays that we are shooting, but based on the proximity between the ray that we are shooting and also the latent features that define with the voxels, we can basically update only those kind of small set of the parameters, which makes the training to be way more efficient. But still, we are not directly encoding the opacity and the radiance directly, but still making some encoding them as kind of the latent features. In terms of that, we can do some kind of the compression. So still, we are doing some kind of compression in terms of like decoding those kind of information with the very shallow the layers. So you can say that in terms of like, to handle this kind of like trade-off between the computation time and the memory, we are still like going back to the some voxel plus some kind of the latent feature the representation in terms of that. Still, we are having some kind of the some per voxel some information, but those are also decoded with the shallow the layers, shallow the network. The way that we can make some kind of the balance between these two. So yeah, so you can see that the feature vectors are like linearly interpolated. And then, so previously, like we are interpolating the opacity and the radiance directly, right? But now we interpolate the feature vectors, and then those are basically decoded with the very shallow network. So this is kind of the comparison with all the cases that basically, we are basically having no encoding. So it's kind of like the previous case. We are directly storing the opacity and the radiance information in the 3D grid for the same amount of the memory. So it's not giving some kind of good quality. But when you basically have some kind of the single network encoding everything into the neural net parameters, which is kind of like giving some kind of the good quality, but basically taking way more time for the computation. But when you have some kind of the some hybrid representation, having the voxel the resolution of the 128 cubic, and also the feature dimension of the 16, and also having some shallow network for the decoding, it's kind of making some kind of good quality. So compared to this, is just taking so probably 12 minutes to get this, and getting like 1 minute here. So let me switch to the point. Yeah, so compared to the nerve case, taking the 12 minutes, is taking only the 1 minute with some kind of the same quality, but still taking way more kind of the memory for the nerve case, right? So still we want to basically, compress the amount of memory that we are using. So for that, basically what we can also do is that we are not using the single resolution. So this is the case that we're having using the 16, the dimension of the features. But what we can do is that we can also divide this kind of the number of the parameters for some more kind of the global information and the local information. So what we can do is that instead of like using the single resolution, now we're gonna define some kind of the multiple grid with all different the resolution from the 16 cubic to the 173 cubic. So there are some grid which are basically the coarser grid, and there are some other grid which are basically the denser the grid. And then we are basically dividing the feature vector dimension for each of the grid in terms of that every the voxel for each of the grid is now having the 2 dimension, not the 16 dimension. So we can think about it as still kind of like getting some kind of a 16-dimensional feature vector for each of the point. But the 2 out of each of the 16 dimension is coming from the grid with different resolution. Like some 2 dimension of the 16-dimensional vector is coming from the very coarse grid, and the other 2 is also coming from the very fine grid. So in terms of that, we are also basically not using that much kind of the memory for some kind of some global structure by just having some kind of the coarse grid here, but also capturing some kind of the some fine details with some kind of the high resolution grid, while basically allocating some of the dimension of the 16 the dimension vector into that grid as well. Make sense? So this kind of the multi-resolution, the kind of the approach is basically very useful to basically properly allocating the parameters that we are having into some kind of global structure encoded in the low resolution grid, and also the fine details which are also encoded in the high resolution grid. So in this way, we can still get some kind of the very good quality of the outputs while reducing the number of the parameters by having some kind of the some coarser grid as well. So this is some kind of the way that we can basically make the balance of the computation time and also the memory by having some kind of the some latent features and also the multi-grid. And would there be some kind of some other way that we can further increase some kind of the number of the parameters? So it's basically all about some kind of the compression, right? In terms of how we can compress all those kind of the information. And I'm going to skip some details because of the lack of time here. But the thing is that we can basically make some kind of the hash table in terms of that. Now we can also even allow like some of the voxels to have some share the same feature. So let's say like we're gonna have some kind of n sorry, here the thing is that so n is the number of the corner points and t is some kind of some fixed size of the array, right? And then we're gonna basically adding all the features of the n number of the corner points in the array of which size is basically t. So which means that in the hash table kind of a case, there might be some kind of the collision if the size of the array, some kind of hash table is smaller than the number of basically the voxels, the corner points that we are basically encoding. So which means that some kind of the corner points might share some kind of the same feature. So we are basically allowing this to basically compress kind of the things that we are basically encoding in the 3D space. But why still is this kind of okay? Because like we are basically using some kind of the multi-resolution of the grids, which means that even when there are some kind of some 2 voxels that are having some kind of conflict in the hash table of like one specific the resolution of the grid, for the other grid with the different resolution, there would not be some kind of no conflict for those 2 voxels, right? It's basically there will be very rare case that we are seeing some kind of the conflict, like sharing the same features for the 2 corner points for all the resolution. So even when you basically allow some kind of the conflict of some kind of hash table in some certain grid of the resolution, some kind of conflict will not happen for the other cases as well. So when you have this kind of a multi-resolution degrees, we can consider basically compressing all this kind of like latent feature information by setting up some kind of the hash table, which size might be smaller than the number of the voxels, while allowing some kind of the conflicts in the hash table. So what we can see is that in the cursor level of the grid, there will be less likely to have some kind of a collision if we basically limit the size of the hash table, because the number of the corner points will be smaller, right? So there will be no kind of collision. But the thing is that you will only be able to represent some kind of the low resolution the information for the sense. But for some kind of some high frequency, some details, if we use the finer some level of the grid, there will be more likely to have some kind of the collisions across the voxels, but it will be able to basically capture some kind of some fine details. So there are some kind of a trade-off between these two. So by doing this kind of the compression, we can still achieve some kind of the slightly lower, but still kind of good quality, but with some kind of the much fewer number of the parameters. So here we are basically using the 16 megabytes, 16 60 millions of the parameters, while here basically we are using the less than 0.5 million the parameters by using the hash table and doing some kind of compression. And obviously, if we also use some kind of the increase the size of the hash table, then we can get some much better some kind of quality while also taking lots of the memory. So we can see some kind of the memory quality the trade-off in this case. So this is kind of the idea in terms of how we can basically control this kind of the trade-off by using some kind of the multi-grid resolution degrees and also the hash table the idea. Some results of the training. So there is one more technique that we can do some kind of some compression of the 3D voxels, which is based on the SVD. So let me briefly introduce this idea just for the couple of the minutes, and then we're gonna move on to the new topics. So here the basic idea is that in the epipolar geometry, we have seen how we can find the rank 2 matrix which is closest to the given the 3x3 matrix, right? So this is kind of the idea of the low rank approximation. So how we can basically find the low rank matrix which best approximates given some kind of the matrix, right? So for that, basically what we can see is that we can use the SVD. So basically what we can see is that if we see some kind of the multiplication of the U and sigma here, then what we can see is that actually all the matrix can be represented as the sum of the outer product, like this. So if we only use the outer product, that becomes the rank 1, the one rank the approximation of the given the matrix. So this is the one rank the matrix. If you take the sum of these two, that becomes rank 2 the matrix. So it's kind of like low rank the approximation the idea. So in terms of that, what we can do is that given any kind of the matrix, we can basically approximate this kind of the matrix as kind of the sum of the outer products of the pairs of the vectors. And we can do the same thing for the 3D tensor as well. So the 3D tensor is kind of the some extension of the matrix into the 3D space, right? So that's basically 3D grid that we are basically encoding all the information. And then we can do some kind of the low rank the approximation for those kind of tensors by just taking the sum of the outer products of the the vectors. So like this, for each of the dimension here, we are defining this kind of single one-dimensional vectors like this, and taking outer product of those three in terms of that we can do some kind of low rank the approximation. So we can take the sum of those kind of the multiple the outer products of the vector triplets in terms of doing some kind of the low rank the approximations. So basically this idea is that when you assume that the opacity and the radiance information that we are encoding in this 3D space are basically some kind of the low rank the information, instead of directly basically encoding all this kind of per voxel the information, we can represent that as kind of the sum of the outer products. So basically having some kind of some vectors for each of the dimension and taking the outer product, and that becomes the final some kind of the opacity and the radiance information. So this is kind of more algebraic way that we can basically do some kind of the compression of some 3D information that we're encoding using some kind of the 1D vectors and some kind of the outer the products. So you can check out those kind of the details in these slides. So let me skip some details here because of the lack of time. So please check this out yourself. And next time, what we are going to see is that So you can see that those are all the ideas in terms of how we are going to make some combination of some kind of more explicit representation and some kind of the implicit representation. So the NERF was the case that we are purely learning some kind of the implicit neural representation, but now we also can directly encode the opacity and the radiance in the 3D voxels. And we can do some kind of like combination like these two. Basically having some latent feature for each of the voxel in the 3D space and decoding that with some kind of shallow deep network. So these are all kind of the efforts in terms of like make the training to be faster while taking some more the memory, right? So we don't need to use the 3D voxels for that. Actually, we can consider using some kind of the point cloud while basically encoding the latent features for each of the points. And even we can consider using some kind of the mesh representation as kind of the to make the combination like these two. And instead of like making just like having the points, we can basically take a set of some kind of some ellipsoid that is also giving some sort of the volume information in this 3D space as well, to basically get some kind of better results in terms of like faster training while taking some more the memory. So the technique that we are going to discuss next week is about the Gaussian splitting, which is basically one of the very successful example like making this combination in terms of that we can get not only the training time, but also very fast rendering time as well. So these are all the results that we are basically rendering the reconstructed 3D scenes using some kind of the Gaussian splitting the algorithm, which is achieving almost like 60 frames per second the rendering the speed. So next week, we're going to continue the discussion about the hybrid representation and see how we can make some kind of utilize some kind of some sort of ellipsoid representations to achieve some kind of the fast training time and also the fast the rendering time. For some of the details that I skipped for today, please check out the slides and see. And if you have any questions on that, please let me know. Okay. Any questions? Okay, then I will see you next this coming Wednesday in the assignment session. So please come to the classroom for the assignment session. Thank you. Bye.